Now that we've learned several ways to fit our data to various functions, now what we want to do is determine a way to figure out which is the best one to use. Similar to what we did in chapter 2. Um, so if your calculator isn't set for this, you're going to need to go to second catalog, go all the way down to diagnostics on, and then you're just going to want to click on this and hit enter. It's just going to tell you done. Uh, and what this does is it's going to turn on our squared values so that we can see which function best fits this data. So of course we're going to want to put the data in. So if we go to our stat, edit, and clear our lists. By the way, there is a function out there that you can clear all lists, but I just do it this way. So there's 1, 2, 3, 4, 5, 6, and then 1780, 31, 68, 40, 56, 39, 75, 10,000, 38, 76. I don't know why they have to give us such large specific numbers, but 17, 868, 99, and 31, 806, 80. So then we're going to go ahead and first let's quit here and go to our calc, and we have several choices. We can use the linear, quadratic, cubic, and we're going to skip over quartic for this one just for the sake of time. We also have our logarithmic regression and exponential regression, and also our logistic that we learned. So let's just try linear and see what the r squared looks like for that. So if I put linear, and if you have the new calculators, you don't have to type in L1 and L2, but we'll go ahead and do that, and we get a regression r squared of 0.863. So for linear, we get 0.863. Let's try quadratic and put in our lists. So for quadratic, our r squared value is 0.992, which isn't bad. So let's try, let's see here, cubic. We get 0.9998. I'm going to have to start writing the fourth digit out. So 0.9998. And so that would be reasonable enough to predict it. But let's try to see if we get a better fit with some of our other functions. For logarithmic here, we'll put in L1, L2. We get 0.669. So I'll put Ln 0.669. And let's see here. For exponential, by the way, you wouldn't have to do all of this every time. I would actually recommend looking at the graph first to eliminate. If you saw how good this exponential fits, you probably wouldn't bother checking the logarithmic function. But yeah, we see an r squared value of 1, which is honestly probably the first time I've ever seen it more than 0.999. So we have exponential at 1, which I don't know how you beat that. Well, we'll try logistic anyway just to see what it comes out to. Um, so logistic, L1, L2, and it comes out to, logistic always takes a little while. And we actually get an error anyway. So um, it appears that exponential with that 1 r squared value is our best fit. Let's put error here. Um, so that's the approximate, um, I'm sorry, the equation that we want to use. Then we're going to determine the approximate time using that. So if we go back and put in our exponential calculation here, so our exponential regression. So we'll put in L1, L2, and this time I'm going to throw in the variable so we can put it into our graph. So y bar is function y1. So essentially we get y equals almost 1,000 times 1.78 to the x power. And when we graph that, we'll go to zoom stat. And if you would have looked at this data to begin with, you probably would have seen that exponential growth spike. We want to know the approximate time it's going to take to earn a profit of 100,000 in a year. So when I look at my calculator here, I can see that it's probably going to lie between 3, because you get 81.48 at 3.6 years, and 8.2 years, you get over 100,000. So we probably want to zoom in. Another way we can do this is just simply go back and put in our, we know that our equation is y equals about 1,000 times 1.78 to the x power. So if we divide both sides by 1,000, we get y over 1,000. Forgot to write that in. Y over 1,000 equals 1.78 to the x power. And remember, to get out of our exponents here, we can take the log of base 1.78 of both sides. So log base 78 of y over 1,000 equals the same thing over here. The log and the base will cancel out. So essentially, you have log of base 1.78 of y over 1,000 equals x. So if we put in, we want to know 100,000 for y. So log base 1.78 of 100,000 over 1,000. These zeros will cancel out. So really, we just have log 1.78 of 100 equals x. And we can use our change of base form in our calculator to figure out log 100 divided by log of 1.78. And that's going to tell us 7.9 or about 8 years to where we're going to reach $100,000 in a year. So I'm just going to go back to my graph and show you. I'm going to put a manual window in here. This can take some time to figure out, but we're just going to use from 0 to 10. Now that we know what the year is, it's 8, so we'll go 0 to 10 for our years, and for our y values, we can go negative 50,000 to 150,000 because we're trying to see where it's 100,000. So let's try that graph. And you can see we get a nice picture of that exponential growth. If we trace it, you can see year 5, year 6, year 7, and almost to 100,000. We're at 88 grand, 93 grand, and we hit 1,000 between 7.97 and 8.04. So that gives you a really good estimate of about 8 years. So see if you can determine for yourself in this example which one would be the best function to work with.